I think we can start, Marius, and then we proceed with the questions. Just announcement to the participants: we have changed it or mode Zoom. So now we have the webinar option. So if you want to ask a question or say anything, please raise your hand so I can give you the right to, the option to use the microphone for speaking up, or you can use the chat as well. So thank you all for coming. Marius.
Good morning and welcome everybody to our new day of the Brazilian Symposium on Formal Methods and to our keynote by Professor Frits Vaandrager from the Radboud University of Nijmegen in the Netherlands, where he has been a professor since 1995. He got his PhD thesis from the University of Amsterdam in 1990, working with Jan Bergstra. He worked on structural operational semantics and also got seminal results in concurrency theory. He later on did a postdoc at MIT and out of later work together with Nancy Lynch and Roberto Segala, he co-developed I/O automata and hybrid I/O automata. And later on, he became interested in model checking of time systems. He collaborated with the UPAL group, and several extensions to the UPAL tool are due to the research results obtained. He is now leading a research trust on active automata learning. He's heading one of the most high impact research groups in the field. He's been involved in more than 25 European and national research projects, both on theoretical aspects and applications in software engineering. And he's had or is currently advising close to, so a total of close to 30 PhD students. He's heading the Department of Software Science at Radboud University since 2018. is an editor for software tools or technology transfer and logical methods in computer science, and is a very active publisher in high impact publications, having more than 10,000 Google Scholar citations. Recently, he has developed a new algorithm for active automata learning, the L-sharp algorithm, and that's going to be the topic of today's talk. So Frits, welcome, and please take it away.
Okay, yeah, thank you, Marius, for this extensive and nice introduction. It's a great pleasure to give a presentation today, sort of in Brazil. I would have liked to be there in person, but well, that's not possible. We have a not too big group of people attending, so I suggest we keep things quite informal. And if you have at any point questions, please don't hesitate to raise your hand or post questions via the chat, and I will try to address those. This is really a great topic for me to talk about. I've been active in automata learning for more than 10 years now, and so one of the foundations of this area is the L-star algorithm of Dana Angluin, and there have been numerous attempts to improve this algorithm, and often quite successful. The original L-star paper by Dana Angluin has, I think, 2,500 sites, so it's really influential stuff. So we were very surprised when couple of months ago we discovered a new algorithm which is really working in a different way, sort of. So there are also similarities, but it's simpler and it's faster in practice. And so that's something you hope to achieve often, right? That there is this sort of well-known established algorithm, and then you come up with something simpler, which is just as good. So I'm going to talk about that topic today. So my plan is to first give an introduction to the general area and also discuss a bit L-star and the various descendants that have been proposed in the literature. Then I discuss some applications of this active automata learning work. There are many sort of wonderful applications, but still there's something to be improved upon. And so I will discuss the challenges that we derive from these applications. And this will bring me then to this new algorithm, L-sharp, which I will try to explain to you and then conclude. And there are plenty of opportunities for future work. Okay, so basically the type of problem we are trying to solve is that there is some piece of software or hardware, a system under test, and it's a black box. We cannot look inside, and we try to figure out the behavior. So we presume that there is some state machine governing the behavior of this system. And so what we can do is send inputs to the system and observe the resulting outputs, maybe reset the system, do a new experiment, and then we try to come up with sort of a model of what is going on inside. So that's a very fundamental research problem, which one may try to solve, and as we will see, it also has practical applications. So in today's talk, I will assume that the system under test behaves like a Mealy machine. So that means that it's a deterministic system. If I apply the same sequence of inputs twice, I will get exactly the same outputs. And there are no things like timing behavior or probabilities or data parameters. It's a really basic, simple, basic model, and this will allow me to explain the basic principles of learning. So a Mealy machine, just to refresh maybe the definitions. So we fix some set of input events. We have a set of outputs that we may observe. And then a Mealy machine has a finite set of states and some initial states. So here below you see a simple example of a Mealy machine with 3 states. And then the arrow here marks the initial state. And then there are 2 functions. There is a transition function, which given a state and an input specifies the next state. And there is an output function, which for this transition specifies the output. So for instance, if in Q0 an input small a arrives, we will observe a big capital A as an output, and the Mealy machine loops back. So this is the model of Mealy machines, also known as FSMs, that we will work with. And so what is the semantics of Mealy machines? Well, so you can easily define a thing called generalized output function, which for a given sequence, non-empty sequence of inputs, specifies the last output that a Mealy machine will provide in response to this input sequence. Because it will start in this initial state and then do the transitions as specified by the inputs in the sequence. And then for every input, you get a corresponding output, and we're interested in the last one. So we call 2 Mealy machines M and N equivalent if and only if they have the same generalized output function. So if for every sequence of inputs we get the same last output, and therefore all the outputs will be the same, because by taking shorter sequences you will be seeing the previous outputs as well. So this is equivalence. And so if we are learning the behavior of some system under test, we may not expect that we get exactly the hidden Mealy machine that's describing the behavior of the system, but we would like to have something which is equivalent. So something which determines the same output function. So this is a classical problem, which is sort of part of the general area of machine learning. Because in machine learning, we are given a finite set sample of some function, some pairs x, y, and then the task is for the algorithm to come up with a general function from domain X to domain I, which sort of is consistent with all the samples we have observed, and which sort of predicts the function value for also all the inputs that we did not observe. That is the machine learning problem, and that's the situation we're facing here. We for a finite sequence of inputs, we have done experiments, we know the resulting output, but now we want to come up with a general output function, and that is a Mealy machine, described by a Mealy machine, which allows us to predict the general behavior. And so, well, we are talking about Mealy machines, but you can do the same for regular languages. That is sort of a well-known problem, because also these languages can be represented as a function, a function which maps every input symbol to either 0 or 1 in the language or not in the language. And then the task is to come up with for instance, DFA, which matches this language. So already in 1956, Moore, in his famous paper on Gedanken experiments on sequential machines, proposed an algorithm for this learning problem, and he showed it's exponential. There is a well-known thesis by E. Mark Gold on the automata learning problem, or the regular language inference problem. And he showed that So if you are given a finite sample, so a set of words which, and for every word, whether it's in the language or not in the language, then the problem of constructing a minimal DFA that is consistent with all these samples is in fact NP-hard. And the same will also apply to Mealy machines, which is a very similar model. So these problems are difficult. But then in 1987, Dana Angluin had sort of a clever idea, and she came up with an algorithm which may learn an automaton with using a polynomial number of queries. So this was a breakthrough. So let's discuss that idea. So what she proposed is a learning framework where, besides asking whether a word is in the language or not, there is this extra equivalence query, and that makes a big difference. So in our setting, assuming we have a teacher who knows a Mealy machine, the learner may send a sequence of inputs, and then the teacher will respond with the corresponding sequence of outputs. And so the learner may repeat this and pose a number of experiments, and then at some point come up with a candidate state machine. And so then the learner may give this state machine to the teacher, and the teacher will then reply either with yes, meaning that the learner has achieved the task, or the answer will be no, and then the teacher will also give a counter example, and that is a sequence of inputs such that the hypothesis and the hidden model of the teacher have a different outcome. So it's sort of remarkable that actually Dana Angluin, who came up with this framework, was a really good teacher, and she got several prizes at Yale University for her work as a teacher. And if you Google her name, you see testimonies of students who are really excited about how good a teacher she was and how committed to her students. So it's sort of natural that she came up with this setting. And so, okay, I think I explained this. So the two types of queries, output queries and equivalence queries, and how they work. So Dana Angluin tried to come up with an algorithm, which eventually became the L-star algorithm. And it's clear that she was very much inspired by a well-known result from automata theory known as the Myhill-Nerode Theorem. So here I rephrase that theorem in the setting of Mealy machines. So suppose we have some function f, which for a given sequence of inputs gives us an output, such like a generalized output function. Then the Nerode equivalence induced by this function f is a relation between finite sequences, which deems two sequences u and v equivalent if no matter what non-empty sequence w you append to u and v, the same sequence, the final output will be the same. And so basically, this sort of tells us that u and v lead to the same state in a Mealy machine, because from there on, no matter what further inputs arrive, the outputs will be the same. And actually, the Myhill-Nerode theorem says that if any function with which from sequences of inputs to an output is the generalized output function for some Mealy machine, if and only if this function has finitely many equivalence classes. And so that and then the equivalence classes sort of correspond to the states of the resulting Mealy machine. And this well-known result is the basis of the L-star algorithm and of all its successors. Because what Angluin tries to do is to sort of approximate this Nerode equivalence. And she calls two prefixes equivalent unless there is some suffix W which distinguishes them. Okay, so let's illustrate these ideas on an example. So here you see a simple Mealy machine with 3 states, sort of describing a trivial coffee machine. And so in the initial state, you can enter 10 cents. And then after that, if you press a button, you get a coffee. But you may also enter 5 cents twice, because then the total amount of money also is 10, and then get a coffee. And if you sort of have already entered 10 cents, the machine will give you some money in return. Okay, so this is a very simple Mealy machine. And so we can visualize this Nerode equivalence idea by having some huge matrix or table. So where the rows correspond to prefixes and the columns correspond to suffixes. And then in the table, we write down the final output after doing first the prefix sequence and then followed by the suffix sequence. So for instance, if from the empty prefix, we do 5, we get sort of the empty output, because the initial transition here, 5, has the empty output. The same for 10 and B and 2 5s. So initially you don't see anything. But then, for instance, when you first enter a coin 5 and then a coin 10, then the final output will be 5, because you get some money back. Or when you first enter 10 and then press the button, B is the button, then you will observe the C, you get the coffee. So what we can do is for every prefix and every suffix, sort of mark in this matrix the final output if we first do the prefix and then the suffix. So this is going to be an infinite table, infinitely many rows, or infinitely many sequences that you can use as prefix and infinitely many columns. But we will see some patterns because sort of, for instance, if you look at the row for epsilon and the row for B, then you see that the output values written down here are exactly the same, which of course is because when you press the button in the initial state, there is a self loop. So you end up in the same state, and yeah, so clearly the outputs then will be the same for any suffix. So when we look at the rows in this infinite matrix, we see actually that there are 3 different patterns, 3 different types of rows that occur. And these, of course, correspond exactly to the states of the Mealy machine that describes this behavior and the one which we had to learn. So the idea of Dana Angluin was to just build such a table, but of course she couldn't write down an infinite table, so she thought, okay, let's just start with a small table and then sort of grow it until sort of this converges and we can construct an automaton. So this is her idea. She maintains a set of prefixes. So those are the rows in the table. Initially, there's just the empty prefix. And then she maintains a set of suffixes. Initially, these are just all the input events. And so in the table, the rows are either the elements of U or the single letter extensions of elements in U. And these single letter extensions are needed to recover sort of the state of the automaton. And a table is consistent whenever when you have 2 rows, U and V, which are the same, then if I append an input I, they will also be the same. And this is something which we will need because sort of the idea is that when we have such a table, at least initial fragment of it, then we are going to construct an automaton out of it by taking as states the colors of the rows, the equivalence classes of rows which lead to the same outputs. And so if two rows are equivalent and you append an input I to this, then these resulting rows also should be equivalent. Otherwise, you cannot have a sensible automaton construction. And the other requirement is that the table is closed. And closed means that every row that appears as a one-letter extension of U should also appear in U. And if this is not the case, then you just need to extend U. So yeah, I'm not going to spend too much time explaining all the details of the L-star algorithm, but the idea is clear. She tries to construct a fragment of this huge infinite Nerode table. And she starts with a really small one, and then she has some rules for growing the table. And then at some point when the table is closed and consistent, she can construct an automaton. She gives it to the teacher. The teacher will reply with a counterexample, and then all the prefixes of this counterexample are added to as rows. And then Angluin proved that this sort of then eventually will lead to the right automaton. Okay, so that was great. Again, I will not describe the details of the algorithm, but I hope you get sort of the general idea. And then there's been all this work where people try to improve the original algorithm, and often with great success. So the first major optimization was proposed by Ron Rivest and Shapir in 1993. And so the change they made is, rather than adding all prefixes of a counterexample to U, they just added a single suffix to V. And the reason why this was a big improvement is that not all teachers are so helpful as Dana Angluin. And so you may consider a teacher who, when given an hypothesis, sort of returns an incredibly long counterexample. A counterexample containing millions of symbols. And then Dana Angluin in her L-star algorithm will add all the prefixes of this counterexample as rows in the table. So the table will explode. And so Rivest and Shapir had a smarter trick. They just add a single suffix to the table when they get a counterexample. And in order to construct this suffix, they need to do a binary search involving some logarithmic number of membership queries. So this was a big step forward. And then another improvement proposed by Kearns and Vazirani involved use of discrimination trees. The thing is that often when you're filling this huge table, you feel that you do lots of queries which are not needed to figure out what is the target of some transition in the automaton. And so they have a smart notion of a decision tree, which helps to improve that. And then all these things were brought together in work by Isberner, Hauer, and Steffen in 2014 with the TTT algorithm, because they have three trees: a spanning tree, a discrimination tree, and a discriminator trie. And this is really a very efficient algorithm. So in their paper, they claim it's superior to virtually every other learning algorithm. And indeed, it's a very smart algorithm, but it's also complicated. 1 year later, however, there was a master thesis also from Dortmund by Markus Frome, who showed that if you use adaptive distinguishing sequences, so those are sort of output queries where the choice of an input symbol may depend on the outputs that you've received previously. So if you have one output, then you choose to continue the experiment with input A, and otherwise you decide to continue with input B. And this allowed him to speed up even TTT. But the algorithm was really complicated. It has been implemented. It outperforms all the other algorithms on many benchmarks, but yeah, the theory is complicated and has not been published. So yeah, what is the situation? We have the original L-star algorithm, and then you can look at sort of the number of queries you need, which is big O k n square m, where k is the number of inputs, n is the number of states in our automaton, and m is the length of this maximal counterexample. Maybe a better measure of the complexity of these algorithms is sort of the total number of symbols that you need to learn a model, because it makes a difference whether an algorithm needs just a few short output queries comprising of just a few input symbols or really long ones. Doing a long output query will take a lot of time in practice. But so this has a big complexity, and then there's this whole range of other algorithms which have been proposed in the literature, and Eastburner in his thesis gives sort of a good overview of those. So several of those algorithms have been included here. Well, ADT doesn't occur in Eastburner's thesis because it's from a later date. But then what you see is that sort of the most efficient algorithms sort of all agree on the basic worst case query complexity, namely kn square plus n log m. And so if you have this really sick teacher who comes with counterexamples of millions of symbols, you will pay a price, but it's only a logarithmic one. And so therefore in practice, typically you can deal with long counterexamples. Okay, so this is the situation with L-star and its descendants. And these algorithms have been implemented. So there are several tools around which support this stuff, and you can play with those tools. And the most well-known, I guess, is LearnLib from Bernard Steffen and his group in Dortmund. And they implement both active and passive learning algorithms. So passive learning is where you just are given a set of words, and then you have to come up with an automaton. And so they have both active and passive learning algorithms for DFAs and for Mealy machines. And it's pretty easy to use. And okay, but there are also other implementations. So recently, a team in Graz came up with a Python implementation of many of these algorithms. And I think in Grenoble there is a tool, and in Aachen. So there are many implementations. And using these implementations, people have been able to do lots of interesting case studies. So the key idea which allowed us to do case studies is from a paper by Peled, Vardi, and Yannakakis. And they said, okay, look, in practice, when you want to learn a software model, then output queries can be directly answered sort of by the software, because you reset the software, send a couple of inputs, and you observe the outputs. So then a learner may construct an hypothesis, but of course, software is not going to answer whether an hypothesis is correct. But what you can do is to apply a conformance testing algorithm. So this is an area in which Yannakakis had been very active, where so you have this model, and you want to figure out whether an implementation conforms to the state machine model, and you do this by doing tests. And tests basically also are output queries, right? And so you do a lot of them, and then at some point, either you find a counterexample, then you know they are not equivalent, and so you can send a response to the learner, or you give up, right? Because maybe you just don't find a counterexample, time is up. And then what you can do is that the conformance test there sends a yes back to the learner, which is maybe a bit of cheating because the learner is not sure that the correct model has been learned, but you have to stop at some point. So here we see that learning and testing are really sort of complementary activities. The task of a learner is to come up with a hypothesis, and the task of the tester is to debunk this hypothesis and come up with a counterexample. So basically, they are playing a game of science, but in a really restricted domain of Mealy machines. Formulate hypotheses and try to find counterexamples for them. Okay, so this has been used to find bugs in protocol implementations. In Nijmegen, we worked on learning models for the TLS protocol, the TCP protocol, and the SSH protocol. And basically, whenever we look at an implementation, we find some problem. So the implementations typically do not conform to a standard. And sometimes the differences are really worrisome. And as a result, the implementation has to be changed. And so several TLS implementations have been changed as a result of our work. The Linux implementation of TCP has been changed. And so this created impact. This work is useful. And meanwhile, automata learning has been applied to numerous other protocols. And often, if you have someone who's an expert in the protocol and somebody else who knows about automata learning, then within a matter of a few days, you can get automata learning to work. So an application area in which we are interested in Nijmegen, which is sort of different, is to try to learn models of control software from embedded systems. So for instance, we worked with Canon OC, which builds printers, and they have some software controller in all of these printers, and they asked, okay, can you learn a model of it? And we could. It took us quite some time, but here you see a visualization. It is sort of a Mealy machine with a couple of thousand states. And that's not easy, but you can do this. And such models are potentially useful in different ways. Because all these high-tech companies producing embedded software, they have legacy problems. They have problems with legacy software. So these are components which work perfectly well, but they are really hard to maintain because there's no documentation, the original developers left, and so on. So at some point, they need to do something. They, for instance, need to refactor those legacy components. But this is really dangerous because a refactored component may contain mistakes. So then what you can do is, before you replace the legacy component with the refactored implementation, you learn a model from the legacy component. And for instance, you can use this as an observer. And so when the legacy component is replaced by a refactored implementation, you just monitor what the refactored implementation is doing. And whenever it deviates from the behavior of our old trusted legacy component, you raise an alarm. Or you could even go further and block any deviation from the legacy component. And the ideal is then that you learn a model from a legacy component, and then automatically you generate an implementation, a refactored implementation, for which you have a clear model. But that is a difficult thing to achieve in practice. But we did experiments with learning models of controllers with a number of companies. So we worked with Philips on an X-ray scanner. And there the question was, okay, are a legacy component and an implementation, refactored implementation equivalent? And so we just learned models of both of these components, and then we compared the two models using just checking whether they were equivalent. And okay, if they are equivalent, you're yeah, okay, you pass the test. If not, yeah, you have a counterexample between the models. And then what you can do is you can check whether this counterexample also can be reproduced on the implementations. If it can be reproduced, then you've shown that the implementations are different. And if it cannot, then you have found a counterexample for one of the models and you can continue learning. So this is sort of a learning loop which you can apply in practice in these cases. At ASML, I think thus far the largest experiment on automata learning has been applied. So ASML is this big Dutch international company which produces lithographic equipment for building chips. So they have really complicated, huge machines, which you need several trucks to transport them. And these machines contain a lot of legacy software. And so ASML was wondering, okay, can we use automata learning? And then as sort of a experiment, they said, okay, look, for some of our components, we do have models. And so those components have been developed using modern model-based engineering techniques. So show us that you can learn these models from black box implementation. And then you are in business. Then we may apply this on real legacy components. So this was posed as a challenge to the academic community at the Two Olympics challenge in 2019. And this is sort of the situation we get there. So in this plot, what you see, well, every plus sign corresponds to a model for some software component. And on the x-axis, you see the number of inputs of those Mealy machine models. And on the y-axis, you see the number of states of the Mealy machine. So if we move to the right upper corner, we get more inputs and more states. So as long as models have sort of at most 100 models, 100 states, we can learn them. But this is still challenging for current learning technology. So we need to improve our learning algorithms. I think meanwhile, many red pluses have become green. So there is progress in the field, but these examples are still challenging. So conclusions from case studies is that automata learning is sort of an effective bug finding technique, which you can apply in many situations. And so it's becoming sort of a standard tool for software engineers. But yeah, we still need better algorithms because I/O interactions often require a lot of time. And so you want to have as few of these interactions as possible in order to learn a model. And then another observation is that when the models become larger, then the total time needed to learn models is completely dominated by the equivalence oracle, that is by the conformance testing. And we sort of need to better integrate learning and testing if we want to have any chance of dealing with this issue. And then finally, in practice, often you have data values and there's timing behavior. So the model of Mealy machines is a bit too simplistic. So there is still a lot of work to be done, and these are academic scientific challenges. So in the rest of this talk, I will describe this L-sharp algorithm, and that addresses the first challenge and gives some perspective on the second one as well. And so I don't address all problems. The inspiration for L-sharp, and that's sort of interesting, comes from two giants from Dutch science, one being Brouwer, who is the mathematician who is one of the founders of the area of topology, and he founded the area of intuitionistic mathematics. And the other is Edgar Dijkstra, who is well known, for instance, because of his shortest path algorithm. So ideas from these two people helped us to come up with this new algorithm. So let me just explain it. So where L star uses a observation table, the L sharp algorithm uses an observation tree. It just stores all the observations we obtain in sort of a tree. So for instance, here on the right, you see a simple Mealy machine with 3 states. And then on the left, you see an observation tree. And so maybe you press the A button and you got the capital A back. Or you did an experiment BBA, and there you got the results BBC. And so you organize this in a tree. So mathematically, an observation tree is just a Mealy machine, but it's partial because there are some states for which inputs are not defined, and not inputs. All inputs may be defined in all states. And it's also tree-shaped, so there are no loops. And finally, if you have an observation tree for a Mealy machine, then there will be a functional simulation from the tree to the Mealy machine. And it's indicated here by the coloring. Because so at any point during an experiment, the tree is in one state and the Mealy machine is in one state. And then when you continue the experiment, you just can predict the outputs. But the thing is that if you are an experimenter and this Mealy machine is in a black box, then you can observe the tree, but you cannot observe the functional simulation. Now you don't know what states the implementation has, and you don't know these colors, but there's something you can see. You can see that certain states in the observation tree cannot possibly be mapped to the same states in your hidden Mealy machine. And so there we use this idea of apartness. So apartness is a well-known concept in constructive mathematics. And so it's a constructive form of inequality. So two numbers are apart if you have a constructive proof that they are different. You can construct a rational number in between them. So this was proposed by Brouwer more than a century ago. He wrote in German, so it was called örtlich verschieden, Entfernung. And it's Heiting, a student of Brouwer, axiomatized it. So a number can never be a part of itself. And if x is apart from y, then y will be apart from x. And if x is apart from y, then for any number z, either z will be apart from x or z will be apart from y. So recently, my colleagues Herman Geuvers and Bart Jacobs studied apartness in the context of label transition systems and biosimulation. And so they put that on our radar, and so we tried to do the same thing. And so technically, our setting is completely different from what Brouwer is doing, but the idea we use is that we have a focus on apartness, states being different rather than states being equivalent. And we have a focus on constructive evidence that states are apart. So let's look at our example again. So on the left, we have this observation tree for the Mealy machine on the right. I've now left out the colors marking the refinement because we can't see that. So now two states in this observation tree are apart if there is a separating sequence for them. That is, if there is an input sequence for which the outputs are different. So if you look at this automaton, then you can see that states T0 and T3 are apart. And a witness is the input sequence A, because an A in T0 leads to a capital A output, and an A in state T3 leads to a capital C output. So they're apart. Similarly, states T2 and T3 are apart. the same witness. Input sequence A leads to a capital A in T2 and a capital C in T3. And then T0 and T2 are apart because now we have a witness BA. If we do the sequence BA from T0, we get outputs BA. And if we do it from T2, we get outputs BC. So they are different. So we can deduce that these three states are different. We have figured out by these few simple observations that our implementation will need to have at least three states. So this is the mechanism we are using. And then whenever two states are apart in the observation tree, we know that in the hidden implementation, the corresponding states cannot be equivalent. So this apartness relation that we defined is irreflexive, symmetric, but it satisfies a slightly weaker form of this third property. So if you have a witness which shows that R is apart from R prime, and if all the inputs from this witness sigma are enabled in some other state Q, then R will be apart from Q or R prime will be apart from Q, because the outputs must be different. But you cannot conclude apartness for states for which no event is enabled. So in our example, we cannot conclude that T4 is apart from any other state because we know nothing about T4. We have no inputs. But what we can do is we can do an experiment. So we can provide some inputs and, for instance, do the input A in T4, and then we can conclude that T4 will either be apart from T3 or T0, depending on the output. So this is the game we play. And so now we get closer to the structure of L-sharp, which is very similar to Dijkstra's algorithm. Actually, we could almost copy a paragraph from Dijkstra's original 95 paper, 59 paper on the shortest path algorithm. And so during the course of our learning algorithm, we partition the states in the observation tree into three sets. So there's a basis, and the states in the basis form an initial subtree of our observation tree T, and they are pairwise apart. We have witnesses showing the differences, the apartness of all those states. Then there is the frontier. So those are the immediate successors of basis states, which are not in the basis themselves. And then finally, we have the remaining states. And so what the algorithm is doing is it will step by step extend the basis. And then when the basis grows, the frontier will grow along. And yeah, we just keep on doing that until we have learned the automaton. So let's illustrate how this sort of can work. So here you see again our observation tree. There are three states in the basis. They are pairwise apart. I have these witnesses showing they are different. And then there are a few immediate successors. And these are called frontier states. And so what we would like to do is, well, we want to know more about these frontier states. So if we manage to show that a frontier state is apart from all the states in the basis, then we're really happy. Then we have isolated the frontier state, which means we can extend the basis. We can add it to the basis. But we're also happy when we have shown that a frontier state is apart from all the basis states except one. Because then basically we know that sort of if we construct an hypothesis where the states are the basis states, we know where the outgoing transition will go to. So suppose T1 is apart from T2 and T3, but not T0, then in our hypothesis automaton, we sort of know, okay, the A input from T0 will be a self loop back to T0. And so if we have identified the state in the frontier, if it's apart from all states in the basis except one, we know that in our hypothesis model, that one state is where a transition will lead to. So we can use weak cotransitivity to identify frontier states. So because, for instance, state T0 and T2 are apart, so we have a witness showing their behavior is different. So what we can do is use that witness and run it in T1. And then after that, T1 will be apart either from T0 or T2. So this is, and by continuing this game, we can identify frontier states. So let's do it. And so if we take this witness A and run it in T1, we get an output A. Then we know that T1 must be apart from T3. And so by a single experiment, we have increased our apartness relation. We have shown that T1 is apart from T3. And then we can do the other separating sequence for T0 and T2, which was BA, and observe the outcome BA. And then we know that T1 also must be apart from T2, because the output BC is different from the output BA, which we observe here. So we continue like this. We add frontier states if they're missing, and we run the separating sequences for basis states in the frontier states to identify these states. And then once we have identified all the frontier states, we can sort of fold it back and construct an hypothesis. Because for each frontier state, there is a unique state in the basis to which it corresponds. And so that gives us an hypothesis. So and now we arrive at the overall structure of our L-sharp algorithm. Basically, there are 4 rules which we may apply in any order. And so we use Dijkstra's guarded command to express sort of that there's non-determinism in this algorithm. And so the first rule says, okay, if you have found an isolated state in the frontier, a state in the frontier which is apart from any state in the basis, you can just extend the basis. The second rule says, okay, if there is some state in the basis for which has no outgoing I transition, for which the output, there's no outgoing transition for I, then you can just go to that state via its access sequence in the tree, and then do the input, and then you will observe the output. And so then you know a bit more about your target automaton. And then the third rule says, okay, if there are if we have a frontier state, which is not apart from 2 states in the basis, so it's not identified yet, then we just run the witness which shows the difference between the 2 basis states from this frontier state. And then as a result, the frontier state will be apart from either of these 2. And then finally, so if we have no more isolated states and the basis is complete, and so for every basis state and every input, there's an outgoing transition, we can construct a pretty unique hypothesis. And the first thing we can do is to check whether this hypothesis is consistent with the observation tree. Maybe somewhere deep down in the observation tree, there is still some behavior which is not consistent with the hypothesis. So then we get a counterexample for free. And otherwise, we send hypothesis to the teacher, and then the teacher either will answer with yes, and then we have finished learning, or it will answer with a counterexample, which we then need to process. So for reasons of time, I won't go into the details of the counterexample analysis algorithm. Basically, we are inspired by the Rivet-Shapiro trick, where they sort of have a logarithmic number of, they do a binary search in a long counterexample to process it, and so we can do this, and then so after a logarithmic number of output queries, when we have a counterexample, we will manage to isolate one state in the frontier, which will lead to an extension of the basis. So, okay, so why is this algorithm correct? Well, if the algorithm terminates, then it has learned the correct model. That's just because the teacher will say, yes, you've learned the correct model, and the teacher is right. At least that's what we assume. So correctness for our algorithm amounts to proving termination. But termination is sort of easy, because every rule, each of these 4 rules sort of improves something. So either you get an extra state, or you get an extra outgoing input transition for a basis state, or you create a new apartness relation between a frontier state and a basis state. So what we can do is we can define a norm and then show that every application of our algorithm increases this norm. And since the norm induces the number of states in the basis, which has to be less than the number of states in our hidden Mealy machine, this part will terminate. Since we have finally many inputs, this part will terminate. And since there are finally many basis states, and also this part is bounded. So we have a clear quadratic bound on the number of rule applications. And so the complexity of our algorithm, and this is then sort of direct consequence of this norm, is basically the same as the complexity of the best existing algorithms. That is, in the case where we sort of only send an equivalence query, where we apply rule 4, if none of the other rules is applicable. Because if you send equivalence queries all the time, then learning will be really slow. But if you give lower priority to the equivalence queries, then we get exactly the same time complexity as the best existing algorithm. But we can do more. And so one sort of simple speed up which we could define is to use adaptive distinguishing sequences. So I already mentioned them briefly before. And so what is an adaptive distinguishing sequence? That is sort of a decision tree where you present inputs to the system, but depending on the output received for some input, you choose the next one. So here, for instance, we start with doing an input A. If the resulting output is 0, then we continue with another A, but if the output is 1, we continue with a B. So there's not a unique sequence of inputs, it depends on the outputs that we observe. And so the thing is that if we, for instance, take this adaptive distinguishing sequence, we may be able to identify a frontier state, in this case, for instance, T5, using a single query, whereas if we would not be adaptive, but just have preset input sequences, we would at least need 2 of these sequences. So being adaptive helps, and it helps a great deal. And so a key insight was that we can compute an adaptive distinguishing sequence that maximizes the expected number of new apartness pairs directly from the observation tree. And this can be done pretty efficiently. And for reasons of time, I won't go through the technical details of how we do it, but we can compute it directly from the observation tree. And so that gives rise to a slight adaptation of the L-sharp algorithm, where, for instance, if we exercise a new input, then immediately we try to establish as many apartness pairs as possible from the new frontier state to the basis by doing an adaptive distinguishing sequence. And also, when we try to identify the state in the frontier, we use adaptive distinguishing sequences. So this stuff has been implemented. So we wrote a prototype implementation in Rust, and we compared it with implementations in LearnLib of the fastest other known algorithms, TTT, ADT, and Refactoring. We looked at 46 benchmarks from a collection of benchmarks which sort of models that have been learned from real applications. So these are real models from real systems and often have been used to establish standard violations and so on. The benchmarks are relatively small because, well, we still need to scale our prototype implementation, allowing it to deal with larger observation trees. But that is, we believe, an engineering problem. It's not a matter of sort of an exponential problem there. So it's just we need to be able to handle trees with many millions of states. So here are the results. So in this plot, on the x-axis, you see our 46 benchmarks. And then for each of these benchmarks, we have listed on the y-axis on an exponential scale the number of input symbols that we need to learn a model. And we've listed it for a couple of algorithms. So the basic L-sharp algorithm, L-sharp extended with ADS, and then ADT, Refactoring, and TTT. So what do we see? We see that Refactoring is generally the slowest. It needs most queries. And the L-sharp with ADS is sort of generally the fastest. I think there's one instance here where ADT is slightly faster. And then, so TTT and ADT are sort of in between. So these results are pretty nice. We also looked at the total number of symbols needed for learning and testing. So then you also include all the symbols that are needed for conformance testing. And then the picture gets a bit more diffuse. First of all, there is a huge variation in the number of symbols needed when you repeat an experiment. And we repeated every experiment 100 times, but you see the big variance. But still, as a whole, the L-sharp algorithm is performing pretty well. Okay, conclusions. We have this new algorithm, L-sharp. It's based on a couple of key ideas, and most of these ideas already appear elsewhere, except maybe Apartness. And so the idea to use the observation tree as a main data structure also appears in recent work by Susha and Bogdanov. Yeah, sort of using a basis and a frontier as in Dijkstra's algorithm. One could argue that in L star even there, you have this set U and then you have the one letter extension. So the prefixes and their one letter extension. So that's sort of the basis and the frontier. And yeah, the use of adaptive distinguishing sequences also appeared in work of unpublished work of Vrome. So the key new aspect appears to be Apartness. We have the same asymptotic complexities as the best existing algorithm. In practice, we are sort of doing quite well. So what's future work? I already mentioned scaling to handle larger observation trees. We see lots of room for further optimizations. For instance, coming up with short separating sequences, improving the adaptive distinguishing sequences that we compute, etc. Learning and testing is the next step. Because why would you ship an hypothesis once constructed to a conformance testing tool when you have the whole infrastructure, you have this whole observation tree, and why not use the information from that observation tree for determining what test to perform? We would like to integrate active and passive learning. And so the basic structure of L-sharp is similar to algorithms that have been developed for passive learning, where you do state merging on an observation tree. And then I think we want to extend L-sharp to richer settings with register automata, times automata, and so on. Okay, that's it. Thank you. I'm happy to take any questions.
Thank you very much. This has been a very insightful presentation. Thank you for making this both a history of automata learning and combining it with the details of your new work. So, questions from the audience?
It's just you can ask questions with raise your hand, and I can open the mic if you want.
So maybe I can start with a question. I was interested, especially on your last point, right? So does Apartness help compared to Equivalence in enriching the automata, right, with counters, payloads, timers, these things that are essential for real-life systems?
Yeah, we'll have to see. Maybe one thing I could mention is that I discovered L-sharp basically when working on a learning algorithm for register automata. So automata involving data values. And so I came up with this idea of Apartness and sort of started developing that. And then I thought, okay, but this can also be done in a simpler setting of Mealy machines. So let's elaborate that first. Yeah, I hope it will, the approach will be generalizable to richer settings, but that's clearly future work. What I think that in L-sharp we sort of formalize some simple basic ideas, and which many people who worked in the area already had, but we just made it sort of explicit, and now you don't longer have to deal with observation tables and Nerode equivalences. Things become a bit more direct. So I hope it will simplify. And so I was talking to some people who have been working on a learning algorithm for finite automata with counters, and they said, okay, if we would have known about L-sharp before submitting our paper, that's how we would have phrased it. So that also looks promising. But anyway, we still have to see. This paper is now our paper is now under submission at TACAS. We just got the reviews, and so we're optimistic it will make it there. But the paper has to be published, and then other people have to study it and maybe get inspired by it, hopefully.
Thank you. Tiago, you have the view of questions?
Yeah, I think there's one question. I see a raised hand by Sydney.
Sydney, you can speak if you want.
Can you hear me?
Yeah.
Okay. First of all, thank you for your talk. Give a very good overview of automata learning for the ones that are not acquainted with this area. And I found it very interesting. My question is about what kind of systems can be learned using automata learning, because during the presentation, many of the examples were about protocols and some particular kind of system like protocols and printers. And I wonder if it can be used for instance to learn for any kind of system like a web system or a mobile phone application. If there are some restriction, there are some technical restrictions, or can it be used on any kind of system to learn?
Okay, yeah, thanks for an interesting question. So, okay, this is automata learning, right? So what we can learn is control structures. So whenever there is sort of a control structure, there is a system moving between different modes based on internal or external events. Then we can try to explore that using these type of algorithms. So yeah, you could, for instance, also use it to obtain models of graphical user interfaces of websites or mobile phone applications. That would be a possible sort of application area, because also often there you have sort of control structure. You can sort of jump from one mode to another. So when there is an intricate dependency between control and data, and sort of specific complicated information about your data parameters determine to which control modes you jump, then learning may become, the current algorithms have difficulties. But so in many cases, for instance, all these protocols, there are data parameters, but they're just passed around. You pass around data packets. And so in those cases, you can sort of come up with a finite state abstraction from these behaviors. So that is, I guess, the key thing. You have to come up with a abstraction of the system behavior, which is sort of a finite state machine, and you need and this finite state machine needs to be of some interest. I hope this helps a bit.
Okay, yeah, thank you.
Okay, so I would have one more question if possible. You had a really impressive picture of that automata learned from the printer. And you framed this in the context of actually re-implementing legacy software, which is also one of your recent projects. Can you say more about where we are in practice with actually re-implementing something, a control system starting from such a learned model?
Yeah, well, we've done some case studies with industry. At ASML, there was this large case study where they tried to learn models that had been designed using model-driven development. But still, I would think this is in an early stage. So I don't. So in the case of protocols, clearly this technology is very useful, and many people have applied it, found issues, and And so it's ready for use, and you could even think of a company sort of commercializing it. In the case of control software, this is different, because in practice, then yeah, still there are many dependencies between data parameters and control parameters, which somehow are relevant if you want to understand the behavior. And so there, I really think we need to make a step where we can also deal with data parameters and guards and interaction between control and data. And in order to generalize learning to that setting, I think we also need to move gray box. So we cannot treat the software fully as a black box anymore, because otherwise the problem gets too complicated. Yeah, that's what we are working on right now, and I'm optimistic we will get some results there, but the road is still quite long. But then, of course, I mean, there are these occasional case studies where it's just clear that you can apply the technology. In that sense, I think it's similar to model checking, right? You need to have this sort of sense that you know when the technique can be applied and when it cannot. And when you have this sense, in fact, there are quite many cases where you can apply it. But there, I would say model checking is more mature than model learning right now.
Thank you very much. Any more questions from the audience? Well, if not, then let's thank our speaker again for this very insightful keynote. Thiago, do you want to make announcements for the next sessions?
Yes, thank you, Frits. Thank you for the talk. Thank you, Marius. We'll be back at 11 for the second tutorial, which is introduction to that will be useful for this afternoon's technical session. So I hope you see you all here again. We'll maintain this room open so you can stay, and then we can resume at 11. Thank you.
Thank you.